Alright, hello guys, welcome back. I'm your friend in So today we are going to learn the conic sections. What's the meaning of conic?
Conic sections.
Conic sections. Alright. Graphics of circles intro. Let's get into it.
Let's see if we can learn a thing or two about conic sections. So first of all, what are they and why are they called conic sections? Actually, you probably recognize a few of them already, and I'll write them out. They're the circle, the ellipse, the parabola, and the hyperbola, hyperbola. That's a P, hyperbola. And you know what these are already. And I mean, when I first learned conic sections, I was like, oh, I know what a circle is, I know what a parabola is, and I even know a little bit about ellipses and hyperbolas. Why on earth are they called conic sections? So to put things simply, because they're the intersection of a plane and a cone. And I'll draw you down in a second. But just before I do that, it probably makes sense to just draw them by themselves. And I'll switch colors. Circle, we all know what that is. Let me pick a thicker line for my circle. Circle looks something like that. It's all the points that are equidistant from some center. And that distance that they all are, that's the radius, right? So if this is r, and this is the center, the circle is the point, all of the points that are exactly r away from this center. And we learned that early in our educations, what a circle is. It makes the world go round, literally. Ellipse, in layman's terms, is kind of a squished circle. It could look something like this. It could look like, let me do an ellipse in another color. So an ellipse could be like that, could be like that. And it's harder to draw using the tool I'm drawing, but they could also be tilted and rotated around. But this is a general sense. And actually, circles are a special case of an ellipse. It's an ellipse where it's not stretched in one dimension more than the other. It's kind of perfectly symmetric in every way. Parabola, you've learned that if you've taken algebra 2, and you probably have if you care about conic sections. But a parabola, let me draw a line, separate things. A parabola looks something like this, kind of a U shape, and the classic parabola. I won't go into the equations right now, but the classic, well, I will, because you're probably familiar with it. It's y is equal to x squared. And then, it could be, you could shift it around. And I mean, you could even have a parabola that goes like this. That would be x is equal to y squared. You could also rotate these things around. But I think you know the general shape of a parabola. We'll talk more about how do you graph it, or how do you know what the interesting points on a parabola actually are. And then the last one, you might have seen this before, is a hyperbola. It almost looks like two parabolas, but not quite, because the curves they look a little less U-ish and a little more open, but I'll explain what I mean by that. So a hyperbola usually looks something like this. So if these are the axes, and then if I were to draw, let me draw some asymptotes right through, pretty good. These are asymptotes. Those aren't the actual hyperbola. But a hyperbola would look something like this. It could either be it would be like, they could be like right here, and they get really close. They get closer and closer to those blue lines, like that. And it happened on this side too. So it kind of, the graphs show up here, and then they pop over and they show up there. So that would be, this magenta could be one hyperbola. I haven't done true justice to it. Or another hyperbola could be on kind of you could kind of call it a vertical hyperbola, and that's not the exact word, but it would look something like that, where it's below the asymptote here. It's above the asymptote. So this blue one would be one hyperbola, and then the magenta one would be a different hyperbola. So those are the different graphs. So then, the one thing that I'm sure you're asking is, why are they called conic sections? Why are they not called bolas or variations of circles or whatever? And in fact, what's even the relationship? It's pretty clear that circles and ellipses are somehow related, that an ellipse is just a squished circle. And maybe it even seems that parabolas and hyperbolas are somewhat related. This is a P once again. They both have bola in their name, and they both kind of look like opened U's, although a hyperbola has two of these going in kind of opening in different directions, but they look related. But what is the connection behind all of these? And that's frankly where the word conic comes from. So let me see if I can draw a three-dimensional cone. So if this is a cone, let me see. So top, let me draw ellipse for the top. And it has no top. It would actually keep going on forever in that direction. I'm just kind of slicing it so you see that it's a cone, and this could be the bottom. So let's take different intersections of a plane with this cone and see if we can at least generate the different shapes that we talked about just now. So if we have a plane that goes directly, I guess if you call this the axis of this three-dimensional cone, so this is the axis. So if we have a plane that's exactly perpendicular to that axis, so let's see if I can draw it in 3 dimensions. So the plane would look something like this. This is the front line that's closer to you. And then they'll have another line back here. That's close enough. And then, and of course, these are infinite planes. It goes off in every direction. But I'm just trying to. So if this plane is directly perpendicular to the axis of these, so this is where the plane goes behind it, the intersection of this plane and this cone is going to look like this. We're looking at it from an angle, but if you were to look at straight down, if you were sitting here and you were to look at this plane, if you were to look at it right above, if I were to just flip this over like this, so we're looking straight down on this plane, that intersection would be a circle. Now, if we take the plane and we tilt it down a little bit, so if instead of that, we have a situation like this, let me see if I can do it justice. We have a situation where it's like this, other side like this. So that's the plane. Now the intersection of this plane, which is now not orthogonal, or it's not perpendicular to the axis of this three-dimensional cone. If you take the intersection of that plane and that cone, and in future videos, and you don't do this in your Algebra 2 class, but eventually we'll kind of do the three-dimensional intersection and prove that this is definitely the case. And you definitely do get the equations, which I'll show you in the not too far future. This intersection would look something like this. I think you can visualize it right now. It would look something like this, right? And if you were to look straight down on this plane, if you were to look right above the plane, this would look something, this figure I just drew in purple would look something like this. Oh, I didn't draw it that well. It would be an ellipse. You know what an ellipse looks like. And if I tilted it the other way, the ellipse would squeeze the other way. But that just gives you a general sense of why both of these are conic sections. Now, something very interesting, if we keep tilting this plane. So if we tilt the plane, so let's say we're pivoting around that point. So now my plane, it's a good exercise in three-dimensional drawing. Let's say it looks something like this. Go through that. This is my three-dimensional plane. And I'm drawing it in such a way that it only intersects this bottom cone. And the surface of the plane is parallel to the side of this top cone. In this case, the intersection of the plane and the cone is going to intersect right at that point. You can almost view that I'm pivoting around this point, and the intersection of this point and the plane and the cone. Well, this now the intersection would look something like this, and it would keep going down. So if I were to draw it, it would look like this. If I was right above the plane, if I were to just draw it. And there you get your parabola. So that's interesting. If you keep kind of tilting, if you start with a circle, tilt a little bit, you get an ellipse, you get kind of a more and more skewed ellipse, And at some point, the ellipse kind of, the ellipse keeps getting more and more skewed like that. It some kind of pops right when you become exactly parallel to the side of this top cone. And I'm doing it all very inexact right now, but I think I want to give you the intuition. It pops and it turns into a parabola. So you can kind of view a parabola. There is this relationship. It's kind of the parabola is what happens when one side of an ellipse pops open, and you get this parabola. And then if you keep tilting this plane, I'll do it in another color, so it intersects both sides of the cone, my new plane. So if my plane looks like this, I know it's very hard. You wanted the intersection of this plane, this green plane in the cone. I should probably redraw it all, but hopefully you're not getting overwhelmingly
Alright, I must say the quality for this video is quite bad because he is not using any 3D software to help us to understand what he was trying to tell us. But that's fine. Let's say when you see this graph, or why it's called conic sections, because the circle, ellipse, parabola, hyperbola, those four shapes can be generated by making a selection from a conic. And again, what is a conic?
Of these, so this is
what is a conic? Well, the blue line. What is the blue line shapes is an object called conic. Okay, here he was talking about the concept of a circle. How can you define a circle? It's probably very simple. At the beginning, all you have to do is to define the center point. It has to have a position. For example, both have the value of in x-axis and the y-axis. For example, x and y. This is the coordinate of that center point. Then, for define a circle, you have to also define the length, which represents the distance from the center point to the circle itself, something like that. You have to also define this distance. Normally, in China, they would call this distance r, but I guess that's all about the radius or something like that. Yeah, I'm gonna do a search about it. Alright.
Radius.
It's indeed being called radius. But I must tell you frankly that before I learn English, I never know the r has a meaning of radius. Standard equation of a circle. Let's get into it.
The equation of a circle C is x plus 3 squared plus y minus 4 squared is equal to 49. What are its center hk and its radius r? So let's just remind ourselves what a circle is. You have some point, let's call that hk. The circle is a set of all points that are equidistant from that point. So let's take the set of all points that are, say, r away from hk. So let's say that this distance right over here, this distance right over here is r. And so we want all of the set of points that are exactly r away. So all of the points x comma y that are exactly r away. And so you can imagine you could rotate around and all of these points are going to be exactly r away. And I'm going to try my best to draw at least a somewhat perfect looking circle. I won't be able to do a perfect job of it, but you get a sense. All of these are exactly r away, at least if I were to draw it properly. They are r away. So how do we find an equation in terms of r and hk and x and y that describes all these points? Well, we know how to find the distance between 2 points on a coordinate plane. And in fact, it comes straight out of the Pythagorean theorem. If we were to draw a vertical line right over here that essentially is the change in the vertical axis between these 2 points, up here we're at y, here we're k, so this distance is going to be y minus k. We can do the exact same thing on the horizontal axis. The exact same thing on the horizontal axis. This x-coordinate is x, while this x-coordinate is h. So this is going to be x. This is going to be x minus h is this distance. And this is a right triangle because we, by definition, we're saying, hey, this is a vertical, we're measuring vertical distance here. We're measuring horizontal distance here. So these two things are perpendicular. And so from the Pythagorean theorem, we know that this squared plus this squared must be equal to our distance squared. And this is where the distance formula comes from. So we know that x minus h squared plus y minus k squared must be equal to r squared. This is the equation for the set. This describes any x and y that satisfies this equation will sit on this circle. Now with that out of the
All right, so from so far, we have learned about, let's say, 2 things. The first one is that how do you represent if a point is on a circle? Well, you use this sentence. This point is on the circle. Then, after he said all of that, from that we know if the center point is equal to 0.0, 0, then the formula for a circle, or the standard equation for a circle, would be equal to x squared plus y squared equal to r squared. And I must say, all those equations or formulas, they are not invented from nothing. They are invented from previous formula. You know, for example, for this one, it's again derived from the, say, I forgot about the lemma again. Okay, it is derived from the Pythagorean theorem. Okay, this theorem is quite important. I guess, or I think, there has a lot of equations that comes from this theorem in the future that you would meet. Expand the equation of a circle. What is that?
We're asked to graph the circle, and they give us this somewhat crazy looking equation, and then we could graph it right over here. And to graph a circle, you have to know where its center is, and you have to know what its radius is. So let me see if I can change it. And you have to know what its radius is. So what we need to do is put this in some form where we can pick out its center and its radius. So let me get my little scratch pad out and see if we can do that. So this is that same equation. And what I essentially want to do is I want to complete the square in terms of x and complete the square in terms of y to put it into a form that we can recognize. So first let's take all of the x terms. So you have x squared and 4x on the left-hand side. So I could rewrite this as x squared plus 4x. And I'm going to put some parentheses around here because I want to complete the square. And then I have my y terms. I'll circle those in, well, the red looks too much like the purple. I'll circle those in blue. Y squared and negative 4y. So we have plus y squared minus 4y. And then we have a minus 17. And I'll just do that in a neutral color. So minus 17 is equal to 0. Now, what I want to do is make each of these purple expressions perfect squares. So how could I do that here? Well, this would be a perfect square if I took half of this 4 and I squared it. So if I made this plus 4, then this entire expression would be x plus 2 squared. And you can verify that if you like. If you need review on completing the square, there's plenty of videos on Khan Academy on that. All we did is we took half of this coefficient, and then squared it to get 4. Half of 4 is 2, square it to get 4. And that comes straight out of the idea. If you take x plus 2 and square it, it's going to be x squared plus twice the product of 2 and x plus 2 squared. Now, we can't just willy-nilly add a 4 here. We had an equality before, and just adding a 4 wouldn't be equal anymore. So if we want to maintain the equality, we have to add 4 on the right-hand side as well. Now let's do the same thing for the y's. Half of this coefficient right over here is a negative 2. If we square a negative 2, it becomes a positive 4. We can't just do that on the left-hand side. We have to do that on the right-hand side as well. Now, what we have in blue becomes y minus 2 squared. And of course, we have the minus 17. But why don't we add 17 to both sides as well to get rid of this minus 17 here. So let's add 17 on the left and add 17 on the right. So on the left, we're just left with these two expressions. And on the right, we have 4 plus 17. Well, that's 8 plus 17, which is equal to 25. Now, this is a form that we recognize. If you have the form x minus a squared plus y minus b squared is equal to r squared, we know that the center is at the point a comma b, essentially the point that makes both of these equal to 0, and that the radius is going to be r. So if we look over here, what is our a? We have to be careful here. Our a isn't 2, our a is negative 2. X minus negative 2 is equal to 2. So the x-coordinate of our center is going to be negative 2, and the y-coordinate of our center is going to be 2. Remember, we care about the x value that makes this 0 and the y value that makes this 0. So the center is negative 2, comma 2, and this is the radius squared. So the radius is equal to 5. Radius is equal to 5. So let's go back to the exercise and actually plot this. So it's negative 2, comma 2. So our center is negative 2, comma 2. So that's right over there. X is negative 2, y is positive 2, and the radius is 5. So let's see, this would be 1, 2, 3, 4.
Okay, so far so good. So after you have learned this video, I guess you could probably take a classing in Chinese 高考. I don't know if you know that word or not, but it's just an exam for those students to get into the university. I guess this is just a basic question in that exam. Focus and directory. of whatever.
Focus and directrix of a parabola.
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 Focus and directrix of a parabola. Yeah, it's kind of hard to read. Not even mentioned to understand the meaning of it.
Focus and directrix of a parabola.
Focus and directrix of a parabola. Alright, let's get into it.
What I want to do in this video is understand two words that you might hear associated with parabolas. And that is a focus. That is a focus of a parabola. Focus. And a directrix. Directrix right over there. So what are these things? Well, a parabola can be defined as the set of all points. Let me draw an arbitrary axis right over here. So that's my y-axis. This is my x-axis. This is my x-axis. And so a parabola can be defined as the set of all points that are equidistant to a point and a line. And that point is the focus of that parabola, and that line is the directrix of the parabola. So what am I talking about? So let's give ourselves a point. So let's say this point right over here, and we could even say that that is the point. Let's say that's the point. Let's say the x-coordinate is A, and the y-coordinate is B right over here. So that is the point A, comma B. And then let's give ourselves a line for the directrix. And actually, let me do this in a different color instead of just white, because I already did the coordinates in white. So I will do it in this magenta color. So that's A comma B is the focus. And let's say y equals C is the directrix. So this right over here is the line. Here is the line. Y is equal to C. So this on the y-axis right over there, that is C. This is the line. Y is equal. So a parabola, what does it mean to be the set of all points that are equidistant between a point and this line? Well, let's think about what those points might be. Well, this point right over here would be halfway between this point, between the focus and the directrix. And then as we move away from x equals a, you're going to get points anywhere along this curve, which is a parabola. And you might be saying, wait, I don't get this. I don't get why points along this curve are going to be equidistant. Well, let's just eyeball the distances. So this one, this distance, and obviously I'm drawing it by hand, so it's not going to be completely precise. That distance needs to be equal to that distance. Well, that seems believable. And now this, if we take this point right over here on the parabola, this distance needs to be the same as that distance. Well, that seems believable. If you take this point on the parabola, this distance needs to be the same as this distance. So hopefully you get what I'm talking about when I say that the parabola is a set of all points that are equidistant to this focus and this directrix. So any point along this parabola, this point right over here, this point right over here, the distance to the focus should be the same as the distance to the directrix. Now what you might realize is when you're taking the distance between a point and a
I guess this is a quite new idea about the parabola. I think I have never learned such a thing before in the Chinese classroom, but this is quite new. So the focus of a parabola and the directrix related to the parabola. The directrix here, it's just a line, for example, the purple corner line right in here. And the focus point is what my mouse is pointing at. So these concepts are quite new for me. But what's the point for those concepts? How can we use it to do something? That's a problem.
and a point, you could the distance it'll be at a, I guess you could say it could be at an angle. This one's straight up and down. This one is going from the top left to the bottom right. But when you take the distance from a point to a line, you essentially drop a perpendicular. You essentially go straight down, or if the parabola was down here, you would go straight up to find that distance. These are all right angles right over here. So that's all a focus and a directrix is. And every parabola is going to have a focus and directrix, because every parabola is the set of all points that are equidistant to some focus and some directrix. So that's what they are. In future videos, we'll try to think about how do you relate these points, the focus and the directrix, to the actual equation, or the actual equation for a parabola.
What he said the next is all about the next video. So let's have a look at this video.
I have attempted to draw here in yellow is a parabola. And as we've already seen in previous videos, a parabola can be defined as the set of all points that are equidistant to a point and a line. And the point is called the focus of the parabola, and the line is called the directrix of the parabola. What I want to do in this video, it's going to get a little bit of hairy algebra, but given that definition, I want to see, and given that definition and given a focus at the point x equals a, y equals b, and a line, a directrix at y equals k, to figure out what is the equation of that parabola actually going to be. And it's going to be based on a's, b's, and k's. So let's do that. So let's take a arbitrary point on the parabola. Let's say we take this point right over here, and its x-coordinate is x and its y-coordinate is y. And by definition, in order for this to be a parabola, it has to be equidistant to its focus and its directrix. So what does that mean? That means that the distance to the directrix, I'm drawing here in blue, has to be the same as the distance to the focus, which I am drawing in magenta. And when we take the distance to the directrix, we literally just drop a perpendicular, I guess you could say. That's going to be the shortest distance to that line. And then when but the distance to the focus, well, we see that's at a bit of an angle, and we might have to use the distance formula, which is really just a Pythagorean theorem. So let's do that. This distance has to be the same as that distance. So what's this blue distance? Well, that's just going to be our change in y. It's going to be this y. It's going to be this y minus k. It's just this distance. So it's going to be y minus k. Now we have to be careful. The way I've just drawn it, yes, y is greater than k, so this is going to give us a positive value. And you need a non-negative value if you're talking about distances. But you can definitely have a parabola where the y-coordinate of the focus is lower than the y-coordinate of the directrix, in which case this would be negative. So what we really want is the absolute value of this. Or you could say we could square it, and then we could take the square root, the principal root, which would be equivalent to taking the absolute value of y minus k.
All right, so from this case, or from this equation, we at least know one thing, which is in the mathematical world, if they want to get the absolute value of an equation, what they did is to first square it, then take the root of that squared value. But in the programming, what we almost would do is to use a function called ABS, or absolute root value, if you prefer the full length of it.
So that's this distance right over here. And by the definition of a parabola, in order for x comma y to be sitting on the parabola, that distance needs to be the same as the distance from x comma y to a comma b, to the focus. So what's that going to be? Well, we just apply the distance formula, or really just the Pythagorean theorem. It's going to be our change in x, so x minus a squared, plus the change in y, y minus b squared, and the square root of that whole thing. The square root of all of that business. Now, this right over here is an equation of a parabola. It doesn't look like it. It looks really hairy, but it is the equation of a parabola. And to show you that, we just have to simplify this. And if you get inspired, I encourage you to try to simplify this on your own. It's just going to be a little bit of hairy algebra, but it really is not too bad. You're going to get an equation for a parabola that you might recognize. And it's going to be in terms of kind of a general focus, a comma b, and a general directrix, y equals k. So let's do that. So the simplest thing to start here is let's just square both sides so we get rid of the radicals. So if you square both sides, on the left-hand side, you're going to get y minus k squared. You're going to get y minus k squared is equal to x minus a squared plus y minus b squared. Fair enough? Now what I want to do is I just want to end up with just a y on the left-hand side and just x's, a, b's, and k's on the right-hand side. So the first thing I might want to do is let's expand each of these expressions that involve with y. So this blue one on the left-hand side, that's going to be y squared minus 2yk plus k squared. And that is going to be equal to, I'm going to keep this first one the same, so it's going to be x minus a squared. And now let me expand, I'm going to find a color, expand this in green, so plus y squared minus 2yb plus b squared. All I did is I multiplied y minus, I'll see if we can simplify things. So I have a y squared on the left, I have a y squared on the right. Well, if I subtract y squared from both sides, that simplified things a little bit. And now I can, let's see what I can do. Well, let's get the k squared on this side. So let's subtract k squared from both, subtract k squared from both sides. So that's going to get rid of it on the left-hand side. And now let's add 2yb to both sides. So we have all the y. So plus 2yb, that's going to move this, that's going to give us a 2yb on the left-hand side, plus 2yb. So what is this going to be equal to? And I'm trying to run into my graph, so let me give myself a little bit more real estate over here. So on the left-hand side, what am I going to have? This is the same thing as 2yb minus 2yk, which is the same thing. Actually, let me just write that down. That's going to be 2y, do it in green. Well, yeah, why not green? That's going to be 2yb minus 2yk. You can factor out a 2y, and it's going to be 2y times b minus k. So let's do that. So we could write this as 2, or we could write it 2 times b minus k y, if you factor out a 2 and a y. So that's the left-hand side. So that's that piece right over there. These things cancel out. Now on our right-hand side, I promised you a little bit of hairy algebra, so hopefully you see that I'm delivering on that promise. On the right-hand side, you have x minus a squared. And then, let's see, these characters cancel out, and you're left with b squared minus k. These two are going to be b squared minus k squared plus b squared minus k squared. Now, I said all I want is a y on the left-hand side. So let's divide everything by 2 times b, divide everything times 2 times b minus k. So 2 times b minus k. And I'm actually going to divide this whole thing by 2 times b minus k. Now, obviously on the left-hand side, this all cancels out. You're left with just a y. And then it's going to be y is equal to 1 over 2 times b minus k. And notice b minus k is the difference between the y-coordinate of the focus and the y-coordinate, I guess you could say, of the line. Y equals k. So it's 1 over 2 times that, times x minus a squared. X minus a squared. So if you knew what b minus k are, this would just simplify to some number that's being multiplied times x minus a squared. So hopefully this is starting to look like the parabolas that you remember from your childhood. If you do remember parabolas from your childhood. All right, so then let's see if we could simplify this thing on the right. And you might recognize b squared minus k squared, that's the difference of squares. That's the same thing as b plus k times b minus k. Whoops, b minus k. So the b minus k's cancel out.
Well, here he has used a new technique, or let's say equation. For example, if you get an equation like a squared minus, it should be minus a squared minus b squared. If you have an equation like this, actually it could be equal to a plus b times a minus b. Yeah, I don't know where he teaches this stuff, but this equation is just something always would always be true in the mathematics. I just remember this equation from my old experience when doing mathematic problems.
And we are just left with, and we deserve a little bit of a drum roll, we're just left with 1/2 times b plus k. So there you go. Given a focus at the point a comma b and a directrix at y equals k, we now know what the formula of the parabola is actually going to be. So for example, if I had a focus at the point, I don't know, let's say the point 1 comma 2, and I had a directrix at y is equal to, I don't know, let's make it y is equal to -1, what would the formula or what would the equation of this parabola be? Well, it would be y is equal to 1 over 2 times b minus k. So 2 minus -1, that's the same thing as 2 plus 1. So that's 2 times, that's just 3. 2 minus -1 is 3 times x minus 1, x minus 1 squared plus 1/2 times b plus k. 2 plus -1 is 1. So 1. And so what's this going to be? You're going to get y is equal to 1 over 1/6 x minus 1 squared plus 1.
All right. When I look at this equation, I was thinking that I have never seen such an equation before in my education experience. That was strange. But I guess the main point for the learning of mathematics, because it's not about just memorize those equations. That's probably not important, because if you want, you can always do a search and you will find tons of that equations. So the memory kind of things, it's not very important in the mathematics. The most important part is that you have to know to think logically, or know about how can you solve a hard problem, how can you divide a big problem into a lot of small sub-problems, and you solve them one by one. Then you combine your solution together to form the big solution. I guess that's the point of the mathematics learning. Okay, so that's today's learning for the math, and I'll see you guys in the next video. Bye.